Hi Vikas, how are you?
I am good, sir. And how are you, sir?
Yeah, I'm good. I'm good. Where are you from, Vikas?
I am from permanent address. Currently, where I am right now.
Currently, from where are you?
Sir, currently I am from Chandigarh, Base University of Technology,
Okay, okay.
Punjab.
You are in final year BTech?
Yes, sir. I am in final year.
Okay, okay. Good.
Yes, yes.
Yeah, hi. It will be good if you can like turn on the camera. We will interact with each other. Let others join. So you may know me that I am like PhD student in Indian Institute of Science, Bangalore. So here the GATE toppers usually come. So if you want to pursue GATE and for go for higher studies, then this is the good place to come. So what are your ambitions? Like you want to go for MTech or you want to go for PSU?
Sir, actually, we have planned uh, for a PSU as well as MTech.
Okay. PSU as well as MTech. That's good. Like you can, if you want to do go in research side, then MTech is a good option rather than PSU. And if you want to like earn money early, then PSU is a good option. It depends
Yes,
on
sir.
your choice. Yeah, hi Devendra, how are you?
Fine, sir.
Yeah, can you turn on the camera so that we can interact for a bit? Then we can start the session. Like it's up to you. It's not a compulsory thing. Today also like we have four different questions basically on mechanical metallurgy and manufacturing processes. So I will go through the questions one by one and I will give you like sufficient time to solve it before we go to the solutions. That's the same strategy we will apply for this session also. So other in other sessions also they are taking 2014 questions, right? Or 2016 questions. If anyone is attending other sessions. You are muted, Vikas.
Sir, 2014.
2014 they have started. Okay, fine. So this is the second session which I will conduct on 2014 gate questions. So here also, if you have like gone through our previous lectures where most of the questions were of similar pattern only, so these questions are also of similar pattern but asked in a different way. So what I will do is like I will recall the previous year questions, like in 2016 what type of question was asked on the same topic, now how they have transformed the question, and from the same topic how they have asked the question. I will just try to tell you that thing whenever it is required. So I guess like we are 5 minutes 6:05, we can start this session now. So I will project one question which will be of manufacturing processes. If you have learnt manufacturing processes, you can answer that question. So I will project it for like 3 minutes, then we will go through the solution. So
Okay, sir.
I welcome you all for this GET NPTEL session 5 conducted by me. So we will be carrying out 4 questions today, basically on manufacturing processes and mechanical metallurgy. So coming to the first question. So I will give you 3 minutes. If you know all these 4 manufacturing processes, you can answer this question. And I will add on to your knowledge that in all these 4 processes, what kind of defects are usually present. Hence, if other question is asked regarding any particular manufacturing processes, what kind of defect is present in that, then you will be able to answer by just doing this first question. So try to answer this. Deep drawing is a process where you have a punch and you have a sheet and you are pushing that sheet using a punch. That is deep drawing. In rolling, we have two rollers and you pass the sheet in between the two rollers and you reduce the thickness. Forging is basically you have a ram and you have a metal workpiece just below that ram and you are pressing that workpiece using ram, that is forging. And wire drawing is basically you take a cylinder and you just pull through a hole or a nozzle and just to reduce the thickness.
Excuse me, sir.
Yeah?
Sir, have you shared the screen?
No. Oh, just a second. I will share the screen. Thank you for reminding. I just forgot. Okay, can you see my screen now?
Yes, sir.
Yeah, so I will project first question, which is of manufacturing defects. So which one of the following metal forming process is the earring defect associated with? Four options are there: deep drawing, rolling, forging and wire drawing. So if you know like all these processes and the defects associated with each and every process, you can easily answer this question. This is a knowledge based question. I will give you 2 minutes and then we will proceed with the solution. Also, I have given you here the reading material link. If you have not learned the manufacturing processes, then you can go back to these videos on NPTEL so that you know the concept. One minute more and then we will start. Please enter your answer in chat box if you know the answer. Otherwise, we will go through the solution. A. Okay, cool. Anyone is like Manikan is asking, in some days I can't attend your session due to inconvenience of time. Yeah, so I am uploading like in YouTube, on YouTube you can search Swanand Telpande and there you will find all these videos. Like I am uploading every video of every session. So till now I have conducted 4 sessions. I have already uploaded the videos of 3 sessions. Now after completing one more session I will upload further 3 videos on YouTube. So you can search, I will just write, you can search my name. I have put my name in chat box, so you search on that. I guess you will be able to find the videos. Otherwise I will share the link of those videos when I upload it in the next session. Is that fine, Manikan? Yeah, okay, cool. So most of you answered A. So we will go through the solution. This is question number 7, GATE Metallurgical Engineering 2014 question paper. Which of one of the following metal forming processes is the earring defect associated with? Option A is deep drawing, option B is rolling, option C is forging and option D is wire drawing. So first we need to understand like what kind of defects are formed in each and every processes. So first coming to the rolling defect. Here, rolling defect, four kinds of defects are observed. Firstly, like wavy edges will be there, which are the result from the concave roll bending. Sometimes when you pass a sheet through rolls, the rolls bend concavely as well as convexly. Hence, different types of crack or waves will be generated. So, wavy edges on the sheet are formed because of rolling and concave roll bending, and thinner along its edges than its center. So let's say if I have two rolls which are concave, then the center will have higher mass or higher thickness, and the edges will have lower thickness, and the cracks are generated, like you can see these are the center cracks and these are the edge cracks. So this result, like the edge cracks result because of the poor material ductility. Let's say my material is like magnesium and I want to pass it between the rolls. So magnesium or any HCP material has poor ductility. Hence these types of cracks can be observed here. And one of the most important defect in rolling which can be asked in further gate exams is alligatoring. This is because, like let's say if I have a thick sheet and I am passing it through the rolls, what happens is like only the surface of the work is deformed and the bulk of the work piece is not deformed, which leads to like opening of that work piece, which resembles the alligator opening its mouth. Hence this defect is known as alligatoring. So these are the kind of defects which are usually encountered in rolling. Now coming to the forging defects. In forging, what we have is like we have a workpiece and we have a ram from which we are pressing our workpiece. Hence, first is surface crack generation. Like if you are performing forging at low temperatures, this can occur. Like let's say if I have a material which I want to do hot working, but the temperature is not there so that you can easily deform it to 10% of strain or not. Hence, if the temperature is lower than the required temperature, surface crack will nucleate. And if the material is having high sulfur concentration, then also surface cracks will nucleate. Crack at flash, like more prevalent for thinner flash, like penetrates to work. Like what happens is like when you ram it, some material flows out. That material which flows out of the shape is called as flash. And when you cut this material, some crack would always be present here. Hence, this is crack at flash. And internal cracks can be present as you are compressing from one side. You can see here tensile stresses develop in another direction. As tensile stresses develop in a transverse direction, this is your compression direction and this will be your tensile direction. Hence, due to the secondary tensile stresses, internal cracks can be generated in the forging defects. And cold shuts and lubricant residue, all those things come inside forging defects. Coming to the defects in extrusion. What happens in extrusion is like surface cracking or fir tree cracking. So let's say like what happens in extrusion is that you push a workpiece through inside a nozzle, right? So if the friction or speed is high, it may lead to cracking at the surface. So basically this is known as fire tree cracking. And sticking of a billet material on die, and like let's say it is not the die is not perfectly lubricated, then what will happen is like the friction will be more, hence some material of your workpiece will get eroded out because of that friction. Hence the material streaks, pressure also increases and the product stops and then starts to move away. So if you do extrusion, it should be a single flow process rather than start stop. If this thing occurs, then fire tree cracking usually occurs. And internal cracking, which is also known as chevron cracking, happens because like the center of extrusion tends to develop cracks of various shapes because of increasing with it increases with increasing die angle. If say I have a cylinder of 10 mm dia and I need to extrude a 5 mm dia, so the die angle should be high, right? So what happens if you have very high or increased die angle, then center crack will generate in the workpiece. So you have to have a die which will have low angle, like a reduction will be gradual, not drastic. and increases with impurities. Let's say I have a material with lot of impurities, then these impurities act as the crack generating sites. Hence extrusion, like if asked in gate what are the defects in extrusions, you should know fire tree cracking, which is basically the surface cracking, chevron cracking, which is basically the internal cracking. Now coming to the drawing defects. So what happens, this is basically deep drawing defects. Firstly, wrinkling in the flesh. This occurs because of the compressive buckling in the circumferential direction. As you are like punching a sheet, like you can see here, as you are punching the sheet, so the surface of this will wrinkle. This will lead to wrinkling in the flange, and wrinkling in the wall means this thing, option B. And tearing, so sometimes what happens, like you exceeded the pressure sometimes, so what happens, the tensile stresses which are occurred here near the die will lead to generation of crack, which is basically tearing because of high tensile stresses. And earring, what is basically earring, let's say I have a sheet which is firstly rolled, so it has some texture on it. So if texture is present in the material is basically anisotropic, so it will behave differently in different directions. So what happens when the sheet is anisotropic is like, after punching or after deep drawing, you will get such kind of structure. So this wavy nature, after you have drawn a cup using deep drawing, this wavy nature is represented as earring, and it is basically caused because of that the material is anisotropic. And if the punch and die are not smooth, let's say the die is rough, hence surface scratches will be there which can nucleate crack at a later stages. So these are the defects associated with drawing. Hence the correct answer for this question is A, deep drawing, which I guess most of you have answered. Do you have any doubts regarding all the defects of all the processes? If you can learn this slide, it will be better. So any defect, if you are asked, you can easily tell using this slide. Any doubt regarding the defects related to manufacturing processes?
No, sir.
Okay.
No, sir.
Okay, so most of you, like 2-3 people already answered A, deep drawing. So this slide will help you to know all the defects of all the manufacturing processes, and will help you if another question of manufacturing defect is asked. So what I will do is, like, now I will project a second question and you try to answer that question, then we will go through the solution. This is based off the Chauvin's rule. I have taken one question in my previous lecture regarding the Chauvin's rule. I will go back to that question. So what kind of permutation and combinations they can do on a one aspect or one scientific rule, I will tell you that. Try to solve it in 2 minutes. Anyone could get the answer? I will project the last time one question I have solved regarding the same thing. So here what they had asked is for a casting of cylindrical aluminum bloom having a length and like dimensions of the cylinder were given, and you had to calculate the approximate solidification time using the same rule. So we had solved this question previously where you calculated the volume of cylinder first, area of the cylinder first, you had all the dimensions, and you just had to put this in formula and get the solution. Now in here what they have asked is basically they have given that the thickness of solidified layer after 2 minutes is 3 centimeter. Now what will be the solidification thickness after 4 minutes? So in 2 minutes the solidified layer is 3 centimeter. In 4 minutes how much will be the thickness? So this is the difference in on the same concept they can ask in different manner. So that's all they have done. So if you know this formula you can like solve both the questions based on this rule. So if anyone has answered, then we can like solve it here only. Okay, let's begin with the solution. Okay, so this is question number 40, GATE Metallurgical Engineering 2014 question paper. In a sand casting of a rectangular slab, the thickness of solidified layer after 2 minutes is known to be 3 cm. Based on the Chauvinot's rule, the solidified thickness in centimeter after 4 minutes is. So according to the Chauvinot's rule, the solidification time is basically T is proportional to V by A square and K is the mold constant. So basically V by A is proportional to thickness. So we can assume that T, which is time, is proportional to thickness square. So what given is like in 2 minutes 3 cm solidifies. So we have T as 2 minutes. So let's consider T1, which is time, as 2, and the solidified thickness I won't name it as T, I will name it as D. Okay, and D1 is 3 cm. So we have to find out T2 for D2, which is basically we are given T2 which is 4 minutes, and we have to find out D2, how much the solidified thickness is there in centimeter. So basically we will divide this. So what happens, T1 divided by T2 is basically 3. I will write first D1 divided by D2 square. Mold constant will remain constant, so it will get cut. So which is basically 3 by D2 whole square, and T1 by T2 is 2 by 4, which is half. 0.5 is 3 by D2 square. So D2 is basically, so I will take D2 here. D2 square is basically 9 divided by 0.5, which is 18. So under root 18 is 4.24 minutes. So this is the final answer. I hope you understand this question. It's simple only. Any doubts regarding this question? Yeah, Manikam is right, 4.24 centimeter. Could you correlate that V by A can be like it will be proportional to thickness of solidification layer? If not, like I will give you one example. If it is clear, then we will proceed to next question then. How V by A can be correlated to thickness? Okay, so if it is clear, then I will project you the third question. I will give you 2 minutes time, then you can answer that. This is again from extrusion mechanical metallurgy, where the true stress equation is given and you need to find the ideal plastic work of deformation per unit volume in the extrusion process. I will give you 3 minutes. One more minute and then we will go through the solution. Did anyone get? Manikam is asking, can you tell the K value? Regarding previous question or this question you are asking? In earlier question, K was molds constant. So it is irrelevant that the value may be specified, may not be specified, doesn't matter. You have to take just division, and for both the cases the mold constant will be constant, hence the K will vanish. So it will be T1 by T2 equal to D1 by D2 whole square. Okay, Manikam. It is not required to solve that question. Basically, you have to just to divide that. Hence, k will be cancelled. One thing you guys can do, like in like what I focus on is basically manufacturing processes, mechanical metallurgy, dislocations and everything, some questions of crystallography. So when Wednesday session is there, you just revise few concepts of those things, so you can answer these questions beforehand. So you won't be like you won't require the complete solution to answer that question. That will be better for you guys. So mostly I focus on manufacturing, solidification and everything that comes into manufacturing. What are the defects associated with all the mechanical manufacturing processes, then dislocations, crystallography, like what kind of crystal structures are there, and those kind of things I do. Basically, I won't touch on any question which is related to thermodynamics. That is taken care in some different sessions, which other guys are doing. So if you can read few things before coming to Wednesday session, that will be helpful for you regarding these topics, related to these topics. So okay, we will go to this question then, and we will try to solve this question. I will solve it in front of you only, so you will know how much time it takes to solve this question. This is question number 49, GATE Metallurgical Engineering 2014 question paper. The flow curve of an annealed material is expressed as sigma equal to 200 epsilon raised to power 0.25, where sigma is in MPa. If a rod of this metal is subjected to a true strain of epsilon equal to 0.3 by extrusion, the ideal plastic work of a deformation per unit volume in mj per meter cube is. So consider that you this is your true stress strain curve. So if you are deforming a material, so you are imparting some energy. So this equation is given, which is basically sigma equal to 200 epsilon raised to power 0.25, which is basically Holloman equation. If you have learned this equation, which is K epsilon raised to power n, where K is the strength coefficient and n is the strain hardening exponent. So we have to calculate using this, like extrusion, like till 0.3%. So let's say this point is 0.3. So the ideal plastic work of deformation per unit volume, which will be basically this area. So we have to calculate this area. So how we can calculate is like the ideal plastic work of deformation per unit volume will be basically the area under this curve, which we can integrate this equation from 0 to epsilon, and epsilon higher value is 0.3. So which will be equal to 0 to 0.3. Sigma, we know this equation, so I will directly write it 200 epsilon raised to power 0.25 and d epsilon. So this will be 200 epsilon raised to power 0.25 plus 1 divided by 0.25 plus 1. This is basic integration formula I have applied. So this will be 200 divided by 1.25 epsilon raised to power 1.25, and we know the value of epsilon, which is 0.3, from 0 to 0.3, since like no need for subtraction. So 200 divided by 1.25, 0.3 raised to power 1.25. So I will calculate it. 200 divided by 1.25 is 160 into 0.3 raised to power 1.25, which comes out to be 35.52 mj per meter cube. So this is your final answer, 35.52 megajoule per meter cube. So this is the overall answer, and this is the way to solve it. Basic integration formula you need to know, that's all. And this formula you should know, like the ideal plastic work will be the area under the curve, and you know the equation of curve, then you just have to integrate it from the minimum value to the maximum value, that's all. I hope this is clear.
Yes, sir.
Yeah, good. So some basic formulas are required. So I recommended you last sessions, in previous sessions also. I will recommend you today also that you just have one sheet where you write all the formulas which are required. And as we are solving the gate previous year gate question answers, you know which formulas are required. Like last time, in last question, Chauvin's rule was that formula is required. So that formula here, the Holloman equation, and how you can get this like ideal plastic work of deformation per unit volume, like the area under the curve, that equations you should write in a particular page. And you can have different pages for different subjects, like physical metallurgy, all the formulas in one sheet, mechanical metallurgy, all the formulas in one sheet, like that you can do. Thermodynamics, all the formulas in one sheet. So when you are solving mechanical metallurgy question, if you if you have that sheet with you, you will be able to jot down all the formulas also, and you will be able to recall that formula also easily while solving the questions. So that one assignment, or let's say one exercise you can do, so that you can improve better in these things. Is it fine? For same case in toughness we also calculate, yeah. For same case in toughness also, yeah, toughness is basically the area under the curve. The work done is basically the energy you put into, right. The plasticity is because of the energy which you are giving through in a material. And you are like in extrusion, what happens is like you have a block and you are pushing that block through a die. So what happens is like the amount of energy you are imparting is replicated in two different things. If there is no friction, then you are not working against the friction. Let's say it is a frictionless die. Hence, the amount of energy which you are imparting through a die will directly result into the plasticity of the material. So the area, like the amount of energy which I am imparting, is basically corresponding to the area under the curve, which is like deforming the material. So from this we can be able to know that area under the curve will be the ideal plastic work. That's why this word ideal comes. Like if the die is frictionless, then only ideal will come. Otherwise what will happen? Some energy will be there which will be like getting consumed in working against the friction. I hope you understand that point. Okay, cool. So we will have last question for today's session. If you have any doubts on this question, you can ask.
Yes, sir. Last previous question, sir. Sir, when we are calculating the area.
Okay.
In a stem curve, sir, there is the yield point and the ultimate UTS point, where we calculate from the plastic deformation.
Okay.
So he said you are taking the initial integration 0. So yield point is something greater than 0. So it can affect our answer.
Yeah. So let's say I will draw one curve here. I hope you know like how the yield stress is calculated, right? So if I have a engineering stress strain curve, it will go like this, and
Yes.
0.2,
2.
right?
Yes, sir.
This will be your this thing, means the strain will be 0.002. Okay,
Yes.
so if this you replicate here, it will be near about this only. So we can assume it to be like it is not there also. So like this, the curve will be like this only.
Okay.
I hope you got that point.
Yes, sir.
Why we have taken this?
Yes.
Okay. So this curve will also be like this only. I have shown the plastic behavior regime only here. So let's consider these two things. So I have a stress strain curve like this. So this will be my elastic work, which is usually called as resilience of the material. Okay, and this whole area which comes
Toughness.
will be given by toughness. So if you consider this area and you consider this large area, which is basically like zero point 0.3 is like 30% of your strength. So if you have a block of 10, you are making it like increasing it by 30%. So it is very large. So you can neglect this area as compared to this huge area. I hope I am clear.
Yes, sir.
Yeah. Okay. So coming to the final question of this session, I will just project it. This is the knowledge based question regarding electrodes. Which one of the welding process uses a non-consumable electrode? So if you have studied all the welding processes, then you can easily answer this. Just refer to metal joining NPTEL videos. You will get all the joining processes there. Answer this in 1 minute, then we will just go through the basics of all these four processes. Okay. Okay, we will start with the solution. This is question number 22, GATE Metallurgical Engineering 2014 question paper. Which one of the following welding processes uses a non-consumable electrode? Option A is gas tungsten arc welding. Option B is gas metal arc welding. Option C is submerged arc welding. Option D is flux cored arc welding. So here you can see I have described all the four processes. First process is gas tungsten arc welding. Here the tungsten electrode will be there and you will have a filler rod which will be coming in, near the joint region, and you will have some arc here, and shielding gas will protect this arc and the molten metal or the weld pool from the outside atmosphere so that it does not get contaminated. So here this tungsten filament is non-consumable because you are using filler rod here. So this filler rod is getting melted here and forming the weld pool. Whereas in other techniques, where in gas metal arc welding, this electrode wire is getting consumed, and here in gas metal arc welding we are shielding using shielding gas, hence it is known as gas metal arc welding. Whereas the mechanism remains the same, you will have a electrode wire, however here no shielding gas will be there, here the fused covering flux will be there, which will protect the weld pool from the outside environment. And in flux core arc welding, basically you will have an electrode which is a consumable electrode. On that, the flux core electrode, like the flux will be coated outside the electrode, so that here this is not required, like this like the fuse covering flux which is additionally put is not required in this flux core arc welding. So here in all these four processes, in three processes the electrodes get consumed, and we have to supply, like you can see using these drive rolls we supply additional electrode. This electrode wire is also fed continuously, as because it is consuming here. In this process only the tungsten electrode is the electrode which is not consumed, and we are using filler rod rather than an electrode which is getting consumed. Hence the correct answer is option A, gas tungsten arc welding. I hope these four processes are clear. How shielding is done with different types. My aim is not just to answer that question, I am just introducing or like telling you the concept behind all the four processes, so that if any other question is asked relating to these four processes, you may know like what, in which of the following processes the shielding gas is used, or in which of the following processes cold flux or submerged arc welding what uses what kind of flux or what kind of slag is there which protects the weld pool from the atmosphere. So if this kind of questions which are like somewhat similar can be asked, you will be able to answer the question. So I hope you correctly guessed, only three of you correctly guessed. Difference between the flux cored welding and okay, so here what happens is like in flux arc welding you are melting both. Here the flux is just coated outside the electrode, so here both the things are there. So for that the flux which is present on the outside of the electrode is getting deposited on the outer region, and here this flux is additionally brought in. So here you can see this is the electrode wires which is not containing any flux, so you have to create this region additionally. But in there if you are melting the electrode or causing arc there, this the flux which is like on the outer edge of the electrode will automatically shield it, and because the shielding is done by the flux, the gas is optional. Here you can see it is written that the gas is optional, it is not required because of that. So here additionally you are using flux fused covering flux. Here on the electrode only it is there, hence we don't require additional fused covering flux here. In the lectures you will get to know more differences between these two processes. I have just like told you with the diagram what are the major differences in both the processes. I hope this is clear. Okay, SMAW, shield metal arc welding. I will have to look into it, like I also don't know. So next time maybe I can answer you this question, or you may find it in the reference material. Okay, any more doubt in today's session before I summarize? So let me summarize. So today we like solved questions regarding manufacturing processes and mechanical metallurgy. So two numericals were solved, with simple formulas. Basically, Chauvin's rule, that you need to know, that the formula is like that. And second one was regarding the plastic work, which will be basically the area under the curve. So if you know basic these two formulas, your 2 marks are readily given, like 2 marks you can easily get. And others were knowledge based questions, so you have to read these processes. You need to understand why, what are the differences between these processes, so that you will be able to answer the question. And in manufacturing, I took a question where I explained all the defects in all the manufacturing processes. So let's say if in extrusion it is asked like what kind of defect is present in extrusion, so you will know that it is a fire tree cracking or chevron cracking, that you should know. Or in which of the following processes fire tree cracking is there, so you should know that thing also. So I have tried to cover all the manufacturing processes and their defects. Along with that, we could solve 2 more numericals based on simple formulas. So I guess, I hope you understand, hope you were able to understand today's session. And we will like proceed with 4 more questions of 2014 gate paper only, and then we will move to 2012 gate paper. I hope this is clear. Any question you can ask me, like we have like 5 minutes more. You can ask me regarding to anything, or if you want any more, like what kind of questions you want to have, like numerical based, knowledge based in next session, that also you can tell me.
So I have a question, sir.
Yeah.
So what is the effect of temperature on strain weight? And in hot working process, why the value of N is 0? How can we neglect the value of N?
Value of N is not 0, it reduces actually. So I will like again tell you.
There is some concept of the dislocation motion type. So can you explain in this way?
So I will just brief you, so you will be able to like know the concept. So on this slide I will do that. So what happens is, like, let's say I have a room temperature tensile curve, stress strain curve. So it goes like this and it will go like this, and this will be defined by N, how much hardening happens. So what happens is, like, why the hardening is more at room temperature is, let's say a dislocation is there which is moving on a certain plane. Now it encounters one obstacle. It may be some precipitate, it may be some jog dislocations. Jog dislocations means that dislocation cannot move, or let's say a sessile dislocation. I hope you understand these words, sessile, glissile.
Yes sir, yes sir.
Yeah. So if a gliding dislocation appears here, like encounters this dislocation, these two dislocations will interact with each other. So what will happen is, like, this dislocation cannot easily surpass this dislocation. So let's say this is at room temperature, this T is at room temperature. Now take case of T2, which is well above the room temperature, let's say 500 degrees Celsius. Now this dislocation has enough energy to surpass this dislocation, either by dislocation climb or either by cross slipping. You know dislocation climb and cross slip, right?
Yes sir, yes sir.
Yeah. So from this plane it needs to go to another plane where it can again start gliding. So either this can move out of plane by dislocation climb, which is a temperature control phenomena, or either it can go it can just cross slip and just move. Hence this plasticity. So let's say in the room temperature, the stress required for this dislocation to move, like go around this dislocation, will be higher because thermal energy is not there. And in this case, what will happen is like it already has a certain amount of thermal energy, so the sigma required for this dislocation to jump or cross over this dislocation will be less. So what will happen at this will be, this curve is at room temperature. Now what will happen is like this will be like this, because you require now lesser stress. You require lesser stress for plasticity to occur. Hence the flow stress, when you increase the temperature, the flow stress is basically where more number of dislocations start moving in the material. Till this point, till yield point, no plasticity is there, hence your dislocations are stationary. As soon as this stress is reached, the dislocations start moving and you will get the plastic deformation. So let's say this is at room temperature and this is at higher temperature. That's why less stress is required for plastic deformation to take place, because of the thermal energy component with the dislocation. Hence your strain hardening exponent decreases with increasing temperature. That is basically the funda.
Yes, sir.
Got it?
Yes, sir, I got it.
Yeah. Okay. Any other doubt? Anyone has any other doubt related to this question? So Manikam is recommending numericals in next session. Okay, I will try to have few numericals. Let's see. I have certain amount of questions, from that I need to cover. So if any numerical is left in that like the number of questions, then I will surely take one numerical or two numericals in that. Then shall we close this session?
Sir.
Yeah?
Sir. I have another doubt, sir.
Huh.
So, strain rate is why dominate at elevated temperature?
Strain rate? Like I didn't understand your question. Like
more dominated at the elevated temperature, sir.
Strain rate you are talking about?
Yes.
Okay. Not dominant, because the temperature factor is there. Like at higher temperatures, the dislocations have higher energy to surpass any obstacle. Let's say what happens when you have higher strain rate is that you want dislocation motion in a particular time. Let's say I want 10⁻³ per second is usually the strain rate of tensile test. So I want that particular deformation in that amount of time. So the dislocation needs to surpass the obstacles to get that strain achieved in that particular time. Let's say I am at higher temperature. So in room temperature I will require higher stress to get that strain in that particular time. Whereas at higher temperatures, when you want that particular strain in the same time, you will require lower stress. Hence when you increase the temperature, the strain rate effect decreases, and when you go below the room temperature, it will enhance, because you will require more and more stress to get the dislocations moving and avoiding obstacles to get the same strain in at that time. I hope that is clear, Chintu.
Okay, sir. Yes, sir. Yes.
Yeah. It is basically everything is all the plasticity is dependent on a moment of dislocations and their interaction within a grain, with other dislocations, with precipitates, with grain boundaries, and also like all those things come into picture. Okay.
Okay, sir.
Yeah.
So, sir, it would be right, like if we say if a temperature increases, so dislocation interaction will be less.
It will be more, but what happens is more, let's say you are doing basically only annealing. So annealing has a particular temperature, right? let's say I'm doing annealing of steel, so it is usually done at 800 900 depending on you want to do solution annealing or just stress relieving. Let's say I am doing a stress relieving treatment only. So recovery recrystallization occurs. What is basically recovery and recrystallization? It is basically annihilation of dislocations and for
point defects.
Yeah, point defects and everything. So what happens is, like, if you give a temperature higher, let's say I am doing annealing at 200, I am doing annealing at 400. So my annealing will be good at 400 degrees Celsius because the dislocations are interacting in a better way, right? That's why they are good. That's why they are getting annihilated. So at higher temperature, dislocations will interact more. That's why we are taking a material to a higher temperature for annealing. Otherwise, these dislocations are stationary. If these dislocations are stationary, nothing will happen in material. Okay?
Yes, sir.
Yeah.
But sir, if dislocation interaction will be more, then strain hardening will be more.
No.
But you have told that at high temperature the stress will be less.
That is two different concepts. Like interaction will be more. Let's say I have, like I told you in one aspect, I will tell you in another aspect. So let's say here only. Let's say I am at cryogenic temperature. So this dislocation and this pin dislocation, coming to the last example only, at cryo temperatures this dislocation won't move if the stress is very high. So if this dislocation doesn't come near this, then no interaction will take place, right? Interaction doesn't mean that you are doing strain hardening. Basically interaction means, like, if this dislocation is going in this direction and one opposite sign dislocation is there here, so what will happen? This dislocation and this dislocation will interact and will come at a same point, and as you can see here, this will annihilate. So it doesn't mean that interaction will cause strain hardening. It is not like that.
Okay, sir. But sir, I have studied in the geology data book.
Okay.
There will be mentioned that the reason of the strain hardening is dislocation interaction, and if dislocation interaction will be more, then the strain hardening will be more.
No, it is.
That's why I was asking you.
That was a basic thing. When you will like learn mechanical metallurgy in like upcoming, like in MTech or so, then you will understand. This is like annihilation is also dislocation interaction. So the dislocation, like on broader aspect, you will say like, okay, let's if precipitates are there in my material, then dislocation will interact, it will cause strain hardening. But this is also some kind of interaction only, like the opposite dislocations will interact with each other, they will come just above and below each other and they will annihilate, which means that the overall dislocation density will come down because of interaction of dislocations.
So sir, when a sessile dislocation repel the motion of the other dislocation, so sir, what should we say this process?
Again, like we have one sessile dislocation.
So sir, he will repel the motion of the alag grissile dislocation.
Let's say
so this phenomenon.
So let's say I have a so I will again.
Sir, first case there on their page.
So if sessile dislocation is there, you are saying like one sessile dislocation is there, then
so sir, he will become an obstacle to the dislocation which are moving on the slip.
Exactly.
So sir, this phenomena, what should we say for this phenomena? What is the term we would say for this phenomena? Rather than
Like it is not a phenomena, it is basically comes in the broader domain of interaction of dislocations only, where like how a moving dislocation can encounter a static dislocation, moving dislocations can encounter a dislocation which is moving in opposite direction, means basically this has a negative sign. So there will be different of interactions, so we cannot term this like, it is basically, you can say, a dislocation coming towards an obstacle, that's all we can say.
yes,
And if you have studied interaction of dislocations, there you may see like jogs will be formed, kings will be formed, kings form on a same
yes, sir.
plane, jog form on a different plane. These all things will be given in detail, so you can study that.
Okay, sir.
Okay,
Thank you, sir.
any further doubt?
No, sir.
Okay, if there are no further doubts, then we will like stop this session for today, and we will continue next Wednesday from 6 to 7. Okay, then bye guys, see you next time.